This is a satellite foundational course for GOES-R on derived motion winds. Authors and contributors to this module are listed. I'm Scott Lindstrom from SIMS. Here are the lesson objectives for this module. This is what you'll learn. Derived motion winds are created from 3 sequential images. Features are tracked to estimate the wind necessary to move the feature. 6 different ABI bands are used. Winds are created hourly for the full disk, 4 times an hour for CONUS, and every 5 minutes for mesoscale sectors. A nested tracking technique is used to create visible, infrared, and cloudy water vapor derived motion winds. Small 5 by 5 pixel sub-target scenes are nested within a larger N by N target scene, shown here as 15 by 15. Local motion vectors are derived for the center pixel of each 5 by 5 box. Then this box is shifted by 1 pixel to create another vector, until all 5 by 5 scenes possible are created. A cluster analysis program then subsequently derives the one dominant motion vector for the entire N by N target scene. The final step is to assign a height value to this dominant motion vector. Complete details are in the ATBD linked to at the end of this module. The derived motion winds height assignment process uses the following GOES-R ABI cloud height algorithm, that is ACHA, products: cloud mask and type, cloud top temperature, and cloud top pressure. If the feature tracked is in clear air, for example by using water vapor, then its brightness temperature is used and it's matched to a nearby numerical weather prediction profile of temperature to determine a pressure. Several studies have compared derived motion winds to co-located Rawinsondes, aircraft data, and model winds to compute verification statistics. That comparison is ongoing. This figure compares derived motion winds and Rawinsonde data. There is an overall slow speed bias at upper levels, around 200 hectopascals, because height assignments at that level are often too high. And there's an overall fast speed bias at mid-levels because height assignments there are often too low. Experimental updates to gross error checking and a new version of the GO16 cloud top height algorithm have been evaluated, and those helped the speed bias issues. These changes were implemented operationally during the summer of 2018. This example shows the complementary coverage provided by combining the low-level visible winds, calculated using half-kilometer resolution band 2 0.64 micrometer imagery, and cloud-top water vapor winds, calculating 2-kilometer resolution band 8 6.19 micrometer imagery. The image shows the remnants of Hurricane Beryl off the U.S. East Coast in July of 2018. The visible winds clearly highlight the low-level circulation center, while water vapor winds indicate the presence of a trough aloft, the axis of which is just to the west of the low-level circulation center. These 15-minute CONUS sector visible derived motion winds track the rapid transport of smoke from the Mendocino complex fires as that smoke moved northeastward across California into Nevada. The visible winds, which are calculated from pressure levels at or below 700 hectopascals, showed the smoke moving as fast as 58 knots at 2337 UTC. That speed was nearly twice the speed of all 00 UTC radiosonde winds at or below 700 hectopascals from either Oakland, California, or Reno, Nevada. The derived motion winds here are likely showing a small-scale jet that is unresolved by the radiosonde network. These 15-minute CONUS sector water vapor winds help to quantify the flow within a well-defined upper tropospheric outflow channel northwest of Hurricane Florence. This figure shows 5-minute mesoscale domain sector water vapor winds. The vectors show a trend of improving upper tropospheric outflow in all directions as Hurricane Florence entered a phase of rapid intensification. One of the primary uses of the derived motion wind products is assimilation into numerical weather prediction models. Studies show that proper assimilation results in improved model forecast. One example is more accurate tropical cyclone path forecasts. This particular study from the UK Met Office shows that better 24-hour forecast resulted as more derived motion winds, or AMVs, are assimilated. Derived motion winds can be used in model verification. In this pre-GO16 case, the Ruck model underestimated the intensity of the core of an upper tropospheric jet streak over the southwestern United States. Several wind targets displayed velocity values of almost 180 knots, much faster than the 140-plus knot jet core forecast by the model. Here you see significant differences between the GFS winds and the Himawari 8 derived motion winds. In some cases, the directional difference was as much as 180 degrees. Here is another Himawari case where the low-level derived motion winds were in general agreement with the GFS in terms of the location of the center of a deep mid-latitude cyclone south of Kamchatka. However, east-southeast of the storm center, the derived motion wind showed a backing of winds that highlighted a region of stronger low-level warm air advection that was missed by the GFS. Derived motion winds can diagnose mesoscale features and/or boundaries to aid in situational awareness. In this example from the Hazardous Weather Testbed blog, the winds showed that a favorable vertical wind profile existed ahead of a severe thunderstorm that had just developed over North Texas. Compare the blue low-level winds and the red upper-level winds. Here's another example from the Hazardous Weather Testbed blog showing a pre-frontal trough axis that was oriented from northeast to southwest across Arkansas and Texas. The visible derived motion winds added confidence to the location and movement of this boundary. This slide shall remind you of things you've just heard. For more detailed information on the derived motion winds product, see the Algorithm Theoretical Basis document, the ATBD, at the URL.